In this video, we'll be creating a simple HTTP web server from scratch using Python. You might wonder, why bother creating your own web server, especially a basic one like we'll be creating? While it's true that there's no practical need to build one from the ground up, the process is incredibly educational. It gives you deep insights into computer networking. Remember the old saying, what I hear, I forget. What I see, I remember. What I do, I understand. So, what are the prerequisites to follow this tutorial? All you need to know is Python basics. Remember, we can create our own server in 20 to 30 lines of Python code, which you can find in the GitHub repository mentioned in the description. Due to this, the focus of the tutorial is not going to be about building the web server. In fact, it's going to be about understanding many topics that come along the way, like socket, HTTP, TCP, and more. This is definitely not a deep dive in computer networking, but after you complete this tutorial, I'm sure you'll have a more intuitive understanding of many concepts in networking. So let's get to the main question. What is a web server? A web server is a computer system that stores, processes, and delivers web pages to users. This communication is typically done using HTTP. When you type in a URL in your browser, a request goes out to the web server, which finds the requested page and sends it back to your browser. To me, this concept is kind of weird. Why? Let's say I run some file called index.html by opening it in Chrome. It does run the code and show the content of the web page on the screen, right? So the web server was created, right? Why are we building our own web server? Well, a web server wasn't created here. The browser is simply reading and rendering the contents of the file. If you see the text on the search bar, it begins with file. Now this method of running index.html files is perfectly fine for testing simple websites. However, some things like server-side scripts, databases, or certain JavaScript functionalities do require HTTP and will not work correctly because they require a web server to process the requests. Therefore, we are creating our own web server. Having understood that, let's get into the code. The first thing I want to do is create my own directory where I'm going to create my Python files. So I'll go to the desktop where I'm going to create my Python folder. Let's call this HTTP server. And as you can see, HTTP server was created using the mkdir command, which stands for make directory. After that, I'll change my directory to HTTP server. After that, I'm going to create a main.py file here by using the touch command, touch main.py. After that, I'll do ls just to make sure that my main.py is present in HTTP server folder or not. After that, I'm going to open this entire folder in Visual Studio Code. Now I'm going to open the main.py file and there we go. Now we can start writing our code. So what's the first step? The first step is to create an initializer socket. What is a socket? A socket is an endpoint in a network communication system. They are the most important tool in creating our own server as they allow for the data to be sent and received over the network. They facilitate the connection between the client and the server and enable the server to handle multiple client connections simultaneously. Without sockets, the data communication needed for the operation of a server would not be possible. You might be thinking, what's HTTP then? HTTP is short for Hypertext Transfer Protocol. It is a protocol that's being used when data is sent or received through the sockets. Keep this in mind as it will be useful when we write our own HTTP response. So let's get back to our main.py file and see how we can initialize our socket. So first of all, we'll have to import the socket module that comes built in with the Python environment. After that, to initialize the socket, I'm going to call the socket like this. And there my initialization is done. If you hover over socket, you'll see that it accepts 4 arguments. The first one is family, second type, third proto, and fourth file number. We'll only be passing in family and type. Let's understand what they are. Family accepts a type of address family. And in this address family, we're going to pass in an IP. You might ask, what is an IP? IP or Internet Protocol are rules for routing or sending packets of data across networks between devices. Basically, when data or information travels over the internet or web, it travels in small packets. IP addresses ensure that devices like computers, servers route those data packets to the correct place. So for our family, I'm going to pass in my IPv4 address. To do that, I'm going to pass in socket dot socket.af_inet. This socket.af_inet will specify the Internet Protocol version 4 addresses, the first stable version of IP and also the most used protocol. There is a newer version which is IPv6 and you can use that if you want. The main difference between IPv6 and IPv4 is that IPv4 can generate around 4 billion addresses and IPv6 supports around 340 quintillion addresses. Of course, there are other improvements in performance, but the number of addresses supported in version 4 and version 6 is the biggest problem in IPv4 that led to IPv6. If you want to know more about the differences, I've mentioned an article in the description below which you can check out. The next thing we need to pass into the socket is type, and it accepts a type of socket kind. This type specifies the type of socket we'll be using for this web server. So here I'm going to pass in socket.sock_stream. This means that it is a TCP socket. What is TCP? TCP establishes a connection between the sender and receiver and ensures that the data once it arrives is complete, in order, and error-free. This connection is established using a handshake process in 3 steps. The first step is SYN or synchronize. This means that the client wants to establish a connection with the server, so it sends a packet with the SYN synchronize flag set to the server. This packet includes a sequence number, which is a random number that initiates the sequence numbers for the data packets that the client will send. The second step is SYN ACK or synchronize acknowledgement. So upon receiving the SYN packet, the server responds with a SYN ACK packet. This packet acknowledges the client's SYN packet and includes the server's own sequence number for the data packets it will send to the client. The third step is acknowledgement or ACK. The client receives the server's SYN ACK packet and responds with an ACK packet. This packet acknowledges the server's SYN packet. At this point, the handshake is complete and both the client and server have established a reliable connection. They can now start exchanging data. If you have difficulty understanding this process, think of it this way. Someone knocks at your door, you open the door, they say hi, and your communication begins. Someone knocks at your door, so that's SYN. Then you open the door, that's SYN ACK, and then they say hi, that's ACK. And then your communication will begin. Now over here, instead of using socket.sockstream, you could also use socket.sock_dgram. Sock_dgram specifies that the type of socket we want to use is the UDP socket. UDP stands for User Datagram Protocol. UDP sends packets called datagrams directly to the recipient without verifying whether the recipient is ready to receive or not. So at first glance, UDP and TCP might seem like the same thing, but they're actually quite different. TCP ensures reliable transmission through error checking, retransmissions when the packets are corrupted, and congestion control to reduce traffic load, meaning if the network condition is bad, it will alter the rate of transfer of data. Because of this, TCP is used where reliability and data integrity are critical, such as web browsing and email. UDP doesn't do all of this. It does not establish a connection or handshake before sending data. It sends packets without verifying whether the recipient is ready to receive. The benefit of this is that UDP is faster than TCP as it doesn't have to do error checking. The trade-off is there is no guarantee that the packets will arrive in order, or in fact, they will even arrive. This is why UDP is generally used in applications such as live video, audio streaming, online games, and broadcasting services. So with this, we have initialized our socket. Now I'm just going to store this in a variable. Let's call this server socket. And I'm going to minimize my Explorer here. So I've initialized my socket. The next thing I can do is add some optional settings to change the default behavior of sockets. To do that, I can use this variable server socket and call the setSocketOption method on it. The first thing setSocketOption takes is level, meaning the protocol level for which the configuration is happening. For socket level options, we use socket.sol_socket. For TCP options, we can use socket.ipproto_TCP. We are going to pass in socket.sol_socket. The next thing setSocketOption takes is an option name, meaning the feature we need to enable. Here we will use socket.so_reuse address. SO here stands for socket and reuse ADDR stands for reuse address. This specific option tells the kernel to allow this endpoint to be reused immediately after the socket is closed. Normally, there is a delay before an endpoint can be reused to ensure that any delayed packets in the network are not mistakenly delivered to the wrong application. And finally, the third thing we can pass here is the value. This value is usually either 1 or 0. 1 means on and 0 means off. So obviously, we are going to pass in 1 over here so that we enable the socket reuse address functionality. So simply explained, this line allows the server socket to reuse a local address immediately after the socket is closed instead of waiting for the default timeout. So till now with our 2 lines, great progress by the way, we've created and initialized a socket along with an option to improve performance. Next, we need to connect or more specifically bind a socket to our computer to tell it where our server should listen for incoming requests. This is done using the IP address and port. What is an IP address? Just a bunch of unique numbers and letters that identifies and locates a device on a network. We can access each and every website through an IP address. For example, Google website can be reached by just typing in 142.250.189.206 on the web like this. You see, that number converts to google.com. How? Through DNS. DNS, short for domain name system, is used to map a proper string to this IP address so that we, humans, type only google.com to reach the website instead of a confusing number. Now what is a port? Basically, port helps differentiate between multiple services running on the same computer. It allows computers and servers to route the incoming network traffic to the correct application or service. For example, web servers usually listen on port 80 for HTTP and port 443 for HTTPS traffic. By using different port numbers, a single server can host multiple services, each listening on its unique port, ensuring that all HTTP calls go to port 80 and HTTPS go to 443. Think of it this way. If an IP address is like a company's phone number, then a port number is like an extension. So to bind our socket to an IP address, what we can do is server socket.bind, and here we are going to pass in a tuple. And in this tuple, first is going to be our host and then our port. Now this host is going to depend on you. How do you want this server to be accessible? Well, since I want this server to be accessible from any device, I'm going to pass in 0.0.0.0 like this. If you only want this computer to access the server, you can pass 127.0.0.1. So basically, since I've typed 0.0.0.0, I can access my server from my mobile phone. But if you pass in 127.0.0.1, you'll only be able to access this from your own laptop, from this device, not from anywhere else. After you're done typing in the host, you can pass comma and then specify the server port. For port, you can pass in any number in the range of 0 to 65,535. But remember that ports 0 to 1023 are reserved for the operating system's use, so don't use that. You won't get any error if you pass in any number from 0 to 1023, but your web server will not show up. I'll pass 8080 here because it is very similar to 80. And as I said before, web servers typically listen on port 80 for HTTP request. After we have bound the server to our IP address, the final step is making the socket listen to the incoming connection request using server socket.listen method. So I'm going to pass in server socket.listen like this. How this works internally is that the operating system takes note that this particular socket is now ready to accept incoming connections. It creates a queue for these connections, handling the 3-step initial handshake required. Now you can also specify the size of the queue for the connections by passing in the number over here. As you can see, it accepts backlog. So I'll pass in 5 over here. To be clearer, the backlog parameter, this 5 here, tells the maximum number of fully established connections that can wait in the queue. But wait, what if the queue is full? What will happen to the new connection request? The new connection will either be refused or ignored depending on the operating system and its configuration, causing the client to retry later. So with this, our server is basically created. So I can just print here telling the user that, hey, we have started listening. Okay, so here I'm going to type listening on port, and then you can specify the port on which we are listening. And since we are listening on 8080, I can pass it over here. But what if I change my port later on due to some constraints or something? Well, then I'll have to change it over here, and I might even forget to do so. So what I'm going to do is take this and put it in separate constant variables. So at the top, I'm going to create server_host variable, which is a constant, and that will be equal to 0.0.0.0. After that, I'm going to create server_port variable, which is equal to 8080. And then I can specify server host like this and server port over here. Now I can remove this 8080 and pass the server port like this. And here I'm also going to pass an F so that it becomes an F string, and I can directly pass my server port over here. Also, I'm going to put 3 dots because that's the way I usually do it. Now I can save it. I'm going to open my terminal, and here I'm going to run Python. And if you are on Mac like me and have multiple Python versions installed, you can use Python 3 main.py. And the reason we get this error is because I changed this to a UDP socket using sock_dgram, but we actually want a TCP. So I'll just pass in sock_stream like this. Now I can restart, and you see listening on port 8080 shows up. So that means for a second there, we were listening on port 8080 and a server was created. But the only problem is that we didn't listen to any client connection request and didn't send any data back. That's not how servers work. So let's get into that. Now, if you remember, our connections are getting piled up in a queue. How do I take the front element of that queue? Using server_socket.accept. So I'll pass in your server_socket.accept like this. This will give us a tuple with the socket and the address of the client. So let's extract those two things. I'm going to name socket as client_socket and the address as client_address like this. The socket object is specifically for communication with the newly accepted connection. Don't confuse it with the server socket that we created above. The server socket will continue to listen for other incoming connections, while the new socket is used to send and receive data on the connection we just accepted. The address we receive, the client address, is again a tuple of host and port, just like we had over here. So let's go ahead and print the client socket and the client address one by one, and let's see what they output. So I'm going to open the terminal again, and I'm going to run python 3 main.py, and as you can see, listening on port 8080. Now if I go on localhost 8080 like this and open it, you see the site cannot be reached. However, we get our socket here and the client address over here. So this is the client socket and this is the client host and their port. You see, there was an interesting property over here. When I run my file, we had listening on port 8080 and our program is not over yet. It's still listening on port 8080. However, as soon as I go on localhost 8080 like this, the program closes and it gives us the client socket and the client address. Why? Because the accept will block the code until a connection becomes available, unless the socket is configured to be non-blocking. You can set it to be non-blocking by doing server_socket.setBlocking false on top of the file like this. Now if I save the file and retry this, you see we get an error. The error is blocking IO error, resource temporarily unavailable. Why does the error come in? The error comes in because we told the socket to never block the execution, and when it tried to get a connection request from the queue using this accept method, the queue was empty. So it threw an error. To resolve this, we can use a try and accept block. So I can just do try, then I'll indent this, then I'll have accept, and then I'll just say time.sleep 1. Now to use time, I'll have to import the time module, which I can do at the top. Let me do that real quick. Also, I'm going to print error caught can do something. After that, I'm going to run our code again. And as you can see, listening on port 8080, it delayed for 1 second and then it said error caught can do something. Now, if you really want to make this work, what you can do is run an infinite loop here while true and then indent this. And after you do this, you can just continue simply. So what's going to happen is whenever you catch an exception, you just sleep for 1 second, that means delay it by 1 second, and then you again continue this while loop. So it will keep trying, and once it finally gets the connection request, it will connect, and in a non-blocking way. So I can again run this, and we see listening on port 8080 continuously showing up, no error is showing up, and if I connect like this, I have localhost 8080 and it's loading, but it's never going to show up, and as you can see, we also get client socket and client address showing up in the terminal. And if you're wondering why this is loading, it's loading because it's not able to get the response from the web server. And that's true, we have not sent any response from the web server, so let's get into the process. I'm going to stop this execution. After that, I'm also going to remove all the code for try and except. We're going to keep the while loop as it is. That's because we want to continuously listen for a new connection request. If I just write this much code and remove the while loop, it will listen for just one request. But if I continuously keep an infinite loop, it will listen for multiple connections, not just one. Also, I'm going to remove this sed blocking from here. Make sure to remove that, otherwise the blocking IO error will again show up. So what's the next thing we need to do? Next, we need to get the data, or in our case, the HTTP request from the client so that we can give an appropriate response. To do that, we can use the client socket that's given to us and call the recv function on it, which stands for receive. So I'm also going to remove the print statement here and directly say client socket.recv. And in this, I can specify something known as a buff size. This buff size is the maximum amount of data we can handle in bytes. The most widely used networks limits packets to approximately 1500 bytes. So we can pass in something like that. Many people pass in 1024 and that's fine as well. This recv function, if you see, returns bytes to us as well. Now obviously we can't understand something that's written in bytes. So what I can do is convert it into a string using the decode function, and I can extract the string really nicely. So let me do that. Now, since we have received the string, I can store all of this in a variable and let's call this request. Finally, I can print this request to see what all data are we getting from our request. Now I'm going to open the terminal again, run the code, listening on port 8080. I'll restart this. It still says the page isn't working and it's still loading. However, we get the HTTP request showing up over here. Let's understand this HTTP request over here. One thing to note about HTTP requests and responses is that they have one particular structure. All HTTP requests are composed of a request line, headers, and an optional message body. The first line of the HTTP request is the request line. It contains 3 elements. The HTTP method, in our case it is get, but it can also be post, update, delete, head, and options. Get, as the name suggests, tells or implies that some resource should be fetched. Post suggests that some data is created and pushed to the server. Update and delete mean what the name suggests, updating and deleting. Head is similar to the get method, except that it requests the server to respond with the headers only and not the actual body of the response. Where is that useful? If a URL produces a large download, a head request could read its content length header to check the file size without actually downloading the file. This can save a lot of time. The last HTTP method I want to talk about is options. Options list out the HTTP methods and other options supported by a web server without performing any action or transferring a resource's data. The next part of the first line is usually the URL, but in our case, it is the path, meaning what route of the site is called. For example, if I go to youtube.com/@Revan Ranawat, /@Revan Ranawat is the path of the URL. So in our case, since we passed localhost 8080, it went to /, the default home path for most websites. I'm not going into much detail for this. You can look at the structure to understand more about URL if you want to. The final part of the first line is the HTTP version that was used to send this request. It is 1.1, but there are various versions of HTTP. 0.9, the first official version, 1.0, 1.1, 2, and 3. This versioning might not seem important, but it is actually pretty important. The HTTP version used here determines the structure of the rest of this HTTP request. In version 0.9, request only specified the first two parts of the first line, HTTP method and the path. What about the version? It was the first version, so of course the concept of HTTP versions didn't exist back then. The response was simply an HTML file. No other type of file or message could be sent. In version 1.0, version was added to the first line, headers were attached in both requests and responses. We'll talk more about that in some time. Things like status code and the ability to send files other than just HTML were also added to the response. The biggest problem with version 1.0 was interoperability, meaning different browsers and servers communicating with each other. Why did this issue exist? That's because many people tried to improve the 1.0 version by adding new features. That's good, but there wasn't a good way to make sure all browsers and servers understood these new features. Imagine the issue if I talk to you in English and suddenly say some important information in Hindi. All of this was fixed in the 1.1 version, the first standardized protocol. Along with this, multiple new things were added like cache control, pipelining, meaning the ability to send a second request before the first one is completed. In prior versions, a new TCP connection was created for each HTTP call. As you can imagine, this was inefficient as a web page generally required multiple resources such as images, scripts, and style sheets. The overhead of establishing and tearing down TCP connections for each resource increased the page load times and put more load on the servers. In 1.1, a connection can be or is reused. We will understand how this connection can be reused in a couple of minutes. After that, HTTP 2 was introduced about 15 years later, which focused on improving the performance. HTTP 3 was soon introduced, which focused on changing TCP to QUIC, short for Quick UDP Internet Connection. You can think of QUIC as a protocol built on top of UDP, providing the reliability and ordering of TCP, but with reduced latency and improved performance. How does this happen? Remember, TCP requires a three-way handshake to establish a connection. This adds latency. Additionally, if encryption is done as in HTTPS, there's an additional handshake process. QUIC combines the connection and security handshakes, reducing the initial setup time. How is performance improved? We know TCP connections are identified by IP addresses and port numbers. We did that in our code too. But what if a user's IP address changes, like when they're switching from Wi-Fi to mobile data? Then the TCP connection must be re-established. In QUIC, connections are identified by connection IDs rather than IP addresses, so it doesn't matter if the network or IP changes. All this information is good, but the main question is, why are we getting HTTP 1.1 request, not HTTP 2 or HTTP 3 over here? Simple. We have created a basic server that depends on TCP, because of which HTTP 3 isn't used. In order to run HTTP 3 server, we need to depend on QUIC. What about HTTP 2? To use HTTP 2, we need to implement some other protocols that allow features like multiplexing, meaning the ability to run multiple requests at once. The interesting thing we notice here is the ability of browsers to use HTTP 1.1 to send a request if the server it is interacting with doesn't use HTTP 2 or HTTP 3. Alright, so that's enough about the first line. I promise we'll go over the next lines quicker. To remind you, the lines and structure we will see next are only present in HTTP 1.1 and it might differ in HTTP 2, 3 or the older versions. The next line we have here is host localhost 8080. This specifies the domain name and if you use the IP address, that along with the port of the server from which the resource was requested. The next line is connection keep alive. This tells the server that the client wants to keep the connection open for further requests rather than closing it right after this request is fulfilled. Remember, I had told in HTTP 1.1 a connection can be or is reused. If this line says keep alive, the connection is reused. Next line I want to talk about is this user agent line. This user agent line provides detailed information about the client's browser, operating system, and rendering engine. After that, we have the accept line. This accept line specifies the media types that the client can process, prioritized from left to right. The Q parameter here indicates the quality factor for each type. Then we have SEC fetch mode navigate. This specifies the mode for how the request should be made regarding CORS policies. What is CORS? CORS, short for Cross-Origin Resource Sharing, is a security mechanism implemented by web browsers to protect users from certain types of cyber attacks, like cross-site request forgery. What on earth does that mean? Let's use an analogy. Imagine you have a blog hosted at www.myblog.com and you want to embed a YouTube video within one of your blog posts. The same origin policy is a security measure implemented in web browsers. It ensures that scripts running on pages from your blog can only request data from www.myblog.com and not from any other site directly, like youtube.com. This rule helps protect your blog's visitors from potential malicious scripts and data theft. What do you do in that case? You still want to display YouTube videos, right? That's when CORS enters the scene. It is a mechanism that allows restricted resources on a web page to be requested from another domain outside the domain from which the first resource was served. So if YouTube sets up its servers to include specific CORS headers and responses, it can allow your blog to embed its videos. Essentially, YouTube is telling the browser it's safe to display our video on www.myblog.com. So behind the scenes, when you embed a YouTube video on your blog's page makes a request to www.youtube.com to fetch the video. YouTube servers respond with the video along with the headers that say, we permit www.myblog.com to display this content. The browser checks these permissions and decide if it's okay to show the YouTube video on your blog. The next line we have is SEC fetch dest document. This tells the type of content the client expects to receive as a response. In our case, the request is to navigate the browser to a new document. The next line we have is SEC fetch dest. This tells the type of content the client expects to receive as a response. In our case, the request is to get a document. So the first line was the request line and rest everything we went through were the headers. The third thing in this request is an optional message body. You might wonder, there's no optional message body in our request, right? And that's right, no message body is present in GET requests. However, if it was a POST request, we would have a message body. Let me show it to you. If I go to Thunder Client, and if you want, you can go to Postman. Then I'm going to click on New Request. Then here I'm going to pass in http://localhost 8080. And then I'll put / over here, send a request. It says processing, please wait. And here we see our connection request. However, if I cancel this request, instead of GET, I pass in POST and then send. I get POST written over here. So the HTTP method changes. I'll again cancel the request. And in the body now, in JSON, I'm going to type in my JSON body. Let's say I have a message here which says, hello, what's up? Okay. Then I'm going to send a new request, and you see, after our headers, we have a message body in JSON format saying message, hello, what's up? So a request can also have an optional message body if we want. So that's all about HTTP request format. This was very important to understand, as based on the request, we can frame our response, and this is going to be a piece of cake. So let's quickly get into that. Remember, I had told you that in HTTP version 1.1, all HTTP requests have the same structure. So I'm going to use this to my benefit and extract all the headers. New headers are present on new lines. So to extract all headers, I will split by new line and get all headers in one list. So to do that, I can just do request.split like this. And here I'm going to specify \n. So this will split the request by a new line. And then it will get all the headers in one list. So I'm going to store everything in one list called headers. After that, I'll access the first element of the list to see if it was a get or a post request. So if I just do print headers at 0, this will give me the first line, which is the request line. If I save this and restart my entire application, you see I get the first line get /http/1.1. I can just extract all of this information. The two most essential information for us are the HTTP status method and the path of the URL that was requested. So I'll extract both of them. What I'm going to do is close this terminal and create a new variable called first_header_components, and that will be equal to headers at 0. So that is the first line that we just printed out. And then I'll split by a space. So if I split the thing by a space, that means I get individual elements. Because if you see, we have get space /space http/1.1. So we get all of these three components or elements. So after I get the first header components or first line components, I'm going to access them. So I'll store it in another variable. Let's call this HTTP method, which is equal to first header components at 0. If I do 0, it will tell me the status method. So if it's get, post, update, delete, whatever. After that, I'm going to get the path, which is going to be equal to first header components at 1. Now it's pretty easy, right? I know what kind of HTTP method they're using and on what path are they calling it. So I can just check. If path is equal to /, that means they are coming directly to our home page. In that scenario, I want to return something. So let's say I have an index.html file created over here. And in that, I'm just returning very simple stuff. I'll just say my own server. Then I have, let's say, a simple h1 tag here saying my own web server. And then my p tag, which is saying this is my own web server. Simple. Now I just want to access the elements of this file. So that means all the content that's present within this file. To do that, I can just call the open function that's present in Python, pass in the path, which is index.html, and I want to open this in read format. So I'll not pass anything in the default way. Then I'll store this in a variable. Let's call this file input fin. And then I'll say content is equal to fin.read. Also, I'll close this file for proper measures. And then I'll return the response of the HTTP request. Now, HTTP responses like HTTP requests also have a particular structure to follow. If something goes missing, it generally doesn't give us a right output. The structure of HTTP 1.1 response is something like this. First, the status line. And this status line has three things: the HTTP version, the status code, and an optional text message regarding the status. The second line has some headers passed to it. The headers are just very similar to HTTP request headers, and they're completely optional. You can pass in content type, content length, whatever you want. After that, we have the next line, which is the message body. And this is also an optional thing if you want to pass in some message body. And we are going to pass message body, but we're not going to pass in any headers. So let's follow this HTTP response. So let's create a variable for our response, and this is going to be equal to first the status line. So the status line has the HTTP version, which is HTTP 1.1. If you want, you can also use HTTP 1.0. Very similar structures, since we are returning index.html file. Then we can pass in the status code 200, then an optional message regarding the status, which is OK. Then we are going to leave two lines. So I'll just pass in /n/n like this, and two lines are necessary. Then I'll add the content that we are reading from the file over here, and that's our response. That's it. What does this mean? Well, we have our status line, so the version of the HTTP. Then we have the status code 200. 200 means that everything went well, everything is okay. So it was a success. So here we have also specified our optional text of status. Then we have left 2 lines, which is quite necessary. And I'm also not going to leave any space here. Don't think that would affect anything. Then I'll add the content at the end. Now, how do I return this response? I want to send it back to the client. To do that, there are multiple functions on this client socket that we have. We'll be using sendAll so that all the data is sent to the client. So let's do client socket dot sendAll. And if you see, sendAll accepts data which is readable buffer. But if you see, we have a response in string format and we want to pass the data in readable buffer format. What do we do then? What we'll do is encode the response so that it's converted into bytes. Earlier we had decoded to convert from bytes to string. Now from convert to string to bytes, we're going to do response dot encode like this. And that should send the response to the client. There's another function we could have used, which is the send function. But the problem with it is that there's no guarantee send will send all the data in one call, especially if the message is large or the network is busy. SendAll, on the other hand, continues sending data from the buffer until either all data has been sent or an error occurs. Basically, sendAll handles the resending of data that was not successfully sent in one go. Send doesn't do all of that thing. After that, just make sure to close your client socket just so that you have safe measures implemented. After that, I'm going to run the Python 3 command listening on port 8080. And now if I type localhost 8080, it says my own web server. Here you can see my own server is the title of the document. This is my own web server. So our data or the HTML file is being fetched from our own web server. We've successfully done it. So this was the basic implementation of a web server. Now we can go much more advanced in this. How? Well, if you think about it, right now we are saying if path is equal to slash. That means even if we send a post request, update request, or any other request, it's going to open the HTML file and return it as a response. For example, if I go over here, post it, send it, open the response tab, you see I get the HTML file showing up. Now that might be fine in post request if you want, but what if I put like a delete part and then send it? It's not automatically going to delete anything. It's always going to return this HTML file to us. So how do I make sure that I return path specific content? Pretty easy. We already have the HTTP method extracted. What I can do is just check if HTTP method is equal to get. Only then do I want to run all of this thing. If it's post, I don't want to run any of it. After that, I'll open my terminal and rerun the code. Then I'll go to the new request. Here, I'm going to send the delete request and you see it's still processing. That's because we have sent a post request, so this condition does not match, and we have not put an else condition, so nothing else is being run. So here what I can do is just add an else condition saying if it's not get, no other HTTP method is allowed. So to do that, again I'll frame my response, which is equal to HTTP/1.1. Then I want to specify the error message, which is 405. Then we specify the optional status message, which is method not allowed. Then I pass in /n/n. And then if I want, I can specify the content, and usually it's recommended to put an allow header field in the 405 response. This allow header should contain a list of target resources currently supported methods. Even if you don't put it, it won't really generate an error when we run it. But strict clients or tools that expect you to completely follow the HTTP standards might flag this as an issue or an error. So you are technically violating the HTTP 1.1 specification. If you don't want to do that, make sure to put something like this as a header. Allow get, post. If you're also allowing the post request. I'm only allowing get requests, so I'm just going to put that. After that, I'm going to save it. I'm going to restart my server, go to the new request, then send this. And this is not working because I forgot to do one thing, client socket.sendAll. So I can copy all of these things and paste it in the else condition as well. Or what I can do is just take all of this out from the if condition and put it over here at the same level as this else and if condition. Because here we are specifying a response, here we are specifying a response. So we can access this response variables and encode it and send it across. So I'll save this, I'll restart my server, then I'll send this again, and you see we get a response of allow get. That means we are only allowing get requests. If I put post, send it, again it says allow get, status 405, method not allowed. However, if I put get over here, it will send an HTML file to me with status code 200, okay. Now what if I don't put 1/n over here? What will happen? Let's test it out. If I run the server again, click on new request, send it across, it gives an error. It says parse error, invalid header token. And that's because we've put 1/n, so it thinks that we are specifying a header, and we're not doing that. We are specifying the message body, which is our response, the actual response. So for that, we have to specify 2/n's. Make sure to do that. Then I'll again close my server, restart it, send a response, and it works fine again. Now if you want, you can specify multiple paths as well. For example, right now there's only /. But if I do something like this and send, it still returns this thing because no other route was implemented for HIAH, SIAH, SKNAS, right? So to do that, you can add an elif path over here. Elif path is equal to /book, let's say. And then if the path is book, you want to return some JSON. So let's create a JSON file here. Let's call this book.json, something like this. And then I can do the same thing here. I'll do file opening, reading the content, and then closing the file. And this is going to be book.json like this. Then I'll specify a similar response here. And then we are sending the response anyways, right? So I'll save this. I'll close the terminal, restart again, listening on port 8080. So it again gives me this. But if I put /book like this, you see I get JSON over here. And I get the raw format, parse format. If you're wondering how I got this JSON looking like this, I have a Chrome extension enabled that's called JSON Formatter. So if you want, you can use this. And I get my JSON format also showing up. And if you want, you can implement more paths, more methods, and create a full-fledged server. That is the very basics of creating your own HTTP web server. Now if you want, you can end the tutorial over here. Now I'm going to refactor one part of the code as there's a lot of repetition here. If you see, we are opening the file in this if condition, we are reading the content of the file, then we are closing the file input, then we are framing our response, which is 200 OK, and here we are sending all the response. And we are doing the same thing for the elif condition as well. Now there is repetition, so we need to refactor it. So what I can do is, since the response, file closing, file reading is the same, I'll extract all of this out of the elif condition. I'll do the same thing for the if condition. Only the open file is going to be present in this if elif condition. After that, I can paste all of these things and make sure you indent it nicely. So with this, we open a file and then we are reading the content of the file, whatever that is, closing the file and then framing a response. Now there is a loophole over here, and that is if none of the paths match over here. Now if you want, you can put the else block over here and then handle the edge case here. Maybe you can add a 404 not found response and that should be fine. So that's all about creating your own web server from scratch. Now before we end the tutorial, I have a question for you. How do you make sure that this web server can be used along with several other frameworks? The answer is WSGI, Web Server Gateway Interface. We will look at that in a future video where we create our own backend framework from scratch. So stay tuned for that. Thanks for watching and I'll see you in the next video.